The thing that's fucked is, GPUs fail all the fucking time, right? So, but like, if a GPU in a
Welcome to the hardcore CUDA Hackathon! Woo! Silence and take a seat for a few incredible speakers. My name is Jeremy. Welcome to AGI House. We are going to be creating a stat of phenomenal CUDA projects today. We have for you tried out the Inventor of FlashAttention, Chris Lattner, storied history, and it is an honor to basically bring you an AGI House experience. So the concept here is pretty simple. It is to embody the spirit of Silicon Valley. That is a spirit of creativity and heroism, a spirit of openness and collaborative competition. And I see us as the PayPal Mafia of AI. This is the OG AGI House shop, PayPal Mafia. Myself and Andre Karpathy created this group house, Hillsborough, first of all, which turned into all of the projects and speakers and sort of phenomenal ideas that have come out. You can basically become a part of what is a glorious legacy. So in many cases, people come to our hackathons, they build companies with one another, they end up creating projects that are incredibly impactful on people's lives. So see this as an opportunity to not only have a phenomenal technical experience, but impact the world in a deep way. We're by builders for builders, so everyone who is here is really in the weeds with a lot of technical and creative ideas. We love the researcher, hacker, entrepreneur, and so many of you embody that spirit. This is a body of really incredible people that we've been able to work with. And I hope that the CUDA Hackathon, you can take a creative idea, find someone in this room, and burst it into existence. For a lot of us, hopefully we can get out of our comfort zones, build something, build it fast, make it run well, and ship at the end of the night to an incredible and charismatic audience. So a lot of love for the intentions for the day. I want to first of all thank Ash Vardanian for taking on a lot of the leadership and creating this event. And a big thanks to Nebius, who's about to hand all of you an H100 for the day. Thanks. So with that, Try has created FlashAttention, which is phenomenal advance in being able to quickly and efficiently run our transformers. So he has a few new ideas that he's working on that he'll display to us, but hopefully we get an insight into how the composition of ideas and systems and ideas and transformer architectures can be composed in order to have really, really large impact. So let's hear it for Charlie.
Jeremy, do we want to move the camera over here?
Whatever you think is best. As long as the lighting's good.
Hi everyone. Thanks for having me. I'm really excited to be here today. I'm going to talk about some of the new stuff that we actually just released 2 days ago. So this is, I think, the first public talk on this stuff. So just intro, I'm right now chief scientist at Together AI, also an assistant professor at Princeton. And I'll talk about optimizing attention for modern GPUs. Okay, so just to motivate some of the why we want to do this stuff, why we want to speed up attention. So the problem we're trying to tackle is modeling long sequences, and on the application side, this. All right. Okay. Yeah, so on the application side, this can unlock a bunch of new capabilities. So for example, in NLP, we want to reason over long text for some books and places and code bases. That could be hundreds of thousands or millions of tokens. In computer vision, we want to model high-resolution images. So if you use something like Vision Transformer, high-res images is going to turn into long sequences. In a bunch of new areas like audio, video, medical imaging, data is naturally modeled as sequences of up to millions of steps. And so the dominant architecture right now, the transformer, has some difficulty working with such long sequences. And if we can make attention go fast, we can unlock some of these new areas. And efficiency is the bottleneck for modeling long sequences. So here's just a quick example. This is a while ago. I'm using this is Megatron LM, which is a code base from NVIDIA, used to train large-scale models, and I'm measuring on A100. So if you train a model with sequence length 2K, which was popular maybe 2 years ago, you get very reasonable training speed. But the moment you increase sequence length to 8K, your training speed drops by half or so, or you run out of memory. So if we can solve this efficiency problem, we can train models with much longer sequences. So this is just to motivate why we want to work on this problem. And so that's just motivation. And for the talk, I'll talk about FlashAttention 3, which is the stuff we just released 2 days ago. So I'll recap some of the core ideas of FlashAttention, and then I'll talk about how we optimize that for Hopper GPUs H100. And then I'll show some benchmark results. So just as a background, maybe a bunch of you are familiar already. So the attention mechanism, this is what we're trying to optimize. So as inputs, we're taking query, key, and value. The query and the key and the value have shared n by d, where n is the sequence length, usually on the order of thousands, and d is the head dimension, usually on the order of hundreds. And you multiply them together to get the score matrix, and this score matrix has size n by n. You do a softmax, you multiply by the value to get the output. And so we see that attention scales quadratically in sequence length because of these intermediate matrices of size n by n. So I'm just talking about a single head of attention here. This is why, ever since Transformer came out in 2017, tons and tons of folks have been working on making attention faster, approximating in various ways. Because, it scales quadratically in sequence length n. So if you double the sequence length, you need to do 4x more computation and 4x more memory. So it turns out the biggest cost is not so much in computation, but the biggest cost is in read and writing memory. So it's about moving the bits. And we want to figure out a way to not have to read and write these intermediate n by n matrices. So that was the idea from FlashAttention, combining kind of kernel fusion on the system side and softmax rescaling on the machine learning side that allows us to do this kernel fusion, but still get the right answer. So the idea is to compute things by block. These ideas are quite old, but with attention there are some challenges. For example, the softmax requires this kind of row-wise reduction, and that makes it hard to do kernel fusion. And in the backward pass, if you want to compute gradient, you presumably need to store the intermediate matrices n by n from the forward pass to compute gradient in the backward pass. So our approaches are to use softmax rescaling so that we can do tiling with blocks and then do rescaling to get the right answer. So it's a mathematical transformation of the algorithm, but still gives you the right answer at the end. And for the backward pass, we essentially do recomputation. The idea is you don't want to store large amount of information from memory and having to read and write that. Compute is cheap, so you want to you can recompute things and that end up being faster. So these are two key ideas, and with FlashAttention 1, I think we already had 2 to 4x speed up compared to baseline. And memory is now linear in sequence length, so memory savings is going to go up as the sequence length goes up. So that was maybe 2 years ago. FlashAttention 1 was released 2 years ago, and then a year ago we released FlashAttention 2, which is more optimized for A100, but there's still a problem. So H100 is a challenge because the hardware is new. There's a bunch of new features, and the programming model actually changes quite a bit. So if we just use the old code from FlashAttention 2, we can only get to about 35 to 40% utilization. We can reach maybe 350 teraflops per second, while the H100 max flops is 900. Is around 1,000 teraflops per second. Right. So that is the goal we set out to do, which is to optimize attention for H100 for Hopper. I'm using Hopper as an example. Actually, other accelerators also have this kind of asynchronous programming model that will generalize. So this is joint work with a bunch of folks. Actually started with folks from Kofax, Jay, and Ganesh. There's Ying from Meta. We're very fortunate to collaborate with a bunch of folks from NVIDIA as well. Vijay and Pradeep. Pradeep is here. And I'm just doing cheerleading. Okay, so we want to optimize for H100. What are the new features of the H100 that we care about? There's some new instructions. So there's this warp group MMA that operates at the level of four warps at a time instead of just one warp. That gives you higher throughput. You kind of need to use that if you want to reach the max throughput. There's this hardware unit called TMA, Tensor Memory Accelerator, that lets you do memory loading between global memory and shared memory, and it saves a bunch of registers. So that's important. The other feature, the second feature, is asynchrony, meaning you don't want to have to issue an instruction and then just sit there and wait for it. You can issue an instruction like an MMA, essentially matrix multiply. While the tensor core is computing the matrix multiply, you can go compute something else like the softmax. And Hopper has a bunch of great features to allow you to program asynchronously. So this is the major shift in programming model from the more kind of synchronous programming model in Ampere to asynchronous in Hopper. And to explore that, we have a bunch of scheduling to overlap the matrix multiply and the softmax. I'll talk about why this is necessary. And low precision, FP8. So Hopper supports FP8. This would double your throughput, but it has a bunch of challenges on how you would quantize to reduce quantization error. Okay, so the upshot is once you do all this, you get about 1.6 to 2x on the speed up on FP16, and you get maybe 3x speed up on FP8. Okay, so I'll talk a little bit more details on how these things work. So the new instructions, work group MMA and TMA, you kind of need to use these things. Work group MMA is necessary. If you don't use it, you can only reach about 60-something% of peak throughput. The TMA is a hardware, is a unit in the hardware that will accelerate memory copy between global memory and shared memory, and that saves you a bunch of registers because it does all the coordinate calculation and predication for you. So if you just switch to using these new instructions, you already get most of the way there. I think you can reach about 500 teraflops per second. So you go from 35% to like 50% utilization. But you can go much further. You can exploit asynchrony. So I'll try to motivate why you want asynchrony. So in attention, there are two main operations. One is the matrix multiply, so Q times K, or taking the probability and multiply by V. So these matrix multiply that you need to use tensor cores for. But within the softmax, you need to do these things like exponentiation. You find the max and then subtract the max and exponentiate that. Turns out exponentiation is very, very slow or have very low throughput. Here's an example. I won't go into the details, but because the tensor cores are so fast, within one cycle, I think they can do around per streaming multiprocessor per cycle, they can do around 4,000 operations, right? Because these are specialized hardware units, essentially systolic arrays, to do matrix multiply. But to compute exponential, it has this multifunction unit that has much lower throughput. So the exponentiation has I think 256x lower throughput, right? So even though most of the flops are in matrix multiply, because the throughput of the exponential is so low that it accounts for maybe 50% of the cycle, right? So if you don't overlap these two, you're gonna spend a bunch of time just idling waiting for the exponential while the tensor cores are not running. So we need to overlap them. And so I won't go into details of how we overlap them, but this is just to motivate how exactly you do that. You have to play with the scheduler so that essentially while one work group is doing the tensor core to do matrix multiply, you want the other work group to do the softmax. And that gives you quite a bit of speed up. So for FP8, that would double your throughput, but you got to do a bunch of fancier quantization to reduce error. that I won't go into. I think it's maybe less interesting from a systems perspective, but more interesting on the machine learning perspective. So I won't go to that. The upshot is once you've done all this, you can speed things up quite a bit. So we see about 1.6 to 2x speed up in FP16, and we can reach up to 750 teraflops. So this is pretty much close to the speed of matrix multiply. So that's amazing. You have matrix multiply, which is probably the most optimized subroutine on the planet, and then now attention is getting close. With FP8, we can reach about 1.2 teraflops per second. So that's pretty crazy. And so just to summarize, so this is a fast and accurate attention optimized for modern hardware. The two main ideas are asynchrony and low precision. And with this, you can have faster training, better models with longer sequences. And so for the last couple of seconds or so, I just mentioned if you kind of enjoy this style of work, I'm at Together AI, so we're building a cloud for generative AI. So we do a bunch of stuff, not just low-level optimization, but also model design, architectures, research, and so on. And we're hiring systems research engineer on GPU programming. So if you're interested, go on our website, Together AI. I'm also going to hang around, and if you want to talk to me about this. Right. That's it. Thanks.
The question.
Yeah.
Asynchronous. How backwards compatible does that code end up being, if at all?
It's not so compatible, so it won't run on Ampere. So Ampere, I think with FlashAttention 2, we pretty much reached the limit where it also hit like 70 or 75% util, so there's not a lot to do there. Yeah. Yeah.
Are there open issues or like PRs to go after for people at this hackathon in FlashAttention 3?
So we are still in the process of releasing the code. Some of the code is up there. We're still releasing it. I think it's a little bit too kind of in the weeds, I would say. But if you're interested, I would recommend going through the Cutlass tutorial. I think Pradeep just you guys merged the H100 Jam tutorial.
It's part of the. It's not yet released, but it's there as a PR.
Right. So I would say Cutlass. We build all this on Cutlass. Cutlass is a bunch of tutorials that you can go through as well. Yeah.
How much longer the code base became after you added the asynchrony? Like 10%, 20%?
I think it got shorter.
Oh, really?
Yeah.
Amazing.
I think Cutlass has built a bunch of abstractions that we can use.
Okay.
I think in Ampere, I wrote a bunch of things that I should have just called Cutlass, but now version 3, where we've got Cutlass people telling us like, hey, we already wrote this, you guys should be using it. It makes it quite a bit more pleasant.
And was that growth in compile time due to like the added templates and abstractions from Cutlass?
I think this version is actually very fast to compile because we haven't added all the features like alibi and local attention and so on. So actually right now it takes like 30 seconds to compile. So it's not so bad. The one Ampere has a bunch of features that takes like sometimes like 5 or 10 minutes to compile.
Oh, wow.
Yeah, we're working on that. Yeah. Yeah.
When you're coming up with these creative ideas, like recomputation instead of storage, or like modifying the scheduler, is there like a method where if we're trying this or that to come up with something,
Right.
As useful?
Yeah.
What advice would you have in the process for generating the core idea?
Yeah, so my perspective, I come from a kind of machine learning background, and so the first time I talked to the systems people, kind of the biggest bang for your buck is profiling and benchmarking. Like the first time I talked to someone in the system, they're like, "Did you profile your code?" And that was just mind blowing to me. I did. I was like third year of my PhD, and I'm like, "Yeah, I've never profiled my code. Like I don't know where the bottlenecks are." I can prove to you that it should scale as n log square n something, but I don't know where the bottlenecks are. So profile your code. I think PyTorch has a great tutorial on just PyTorch profiler. That's usually the first thing I reach for.
And when you're profiling CUDA code, how do you typically?
So PyTorch has a profiler. I think NVIDIA also has a pretty good profiler Nsight system for kind of a bunch of kernels, and then Nsight compute for one specific kernel that will tell you where the bottlenecks are. Yeah.
Last question.
Yeah, if you don't mind. So I see that from your presentation, the most of the performance gain you took from synchronous and overlapping.
So how did you practically implement the overlapping so it actually worked, and inside you saw all those kernels running in parallel instead of the hardware schedule puts everything in the queue and the whole performance is just crap. Did you use the Graph API for that implementation, or that's something else?
Right, so it's overlapping at the level of workgroups, so it's one kernel, but you have two main workgroups running, and it will not be apparent how they actually overlap. We use some barrier or synchronization primitive like barrier sync to overlap that, but I don't think there's a good way to visualize that right now. I don't know, Pradeep, if you know, there's a good way to visualize
you can't get a temporal kind of a view of different warps. It's not at that granularity at least.
Right.
Yeah. Okay, thank you.
Yeah. Good. All right.
Thank you. So up next, we have Chris Lattner. I'm sure everyone in the room has used his code with it via LLVM or Swift at some point. Truly storied hacker. So let's hear it for Chris. Woo!
Better at compilers than AV. One second, let me just get on the Wi-Fi real quick. Okay, good. Just load some images.
Attention is all you need.
Yeah. Oh, that's looking a lot better. Needing to be connected. It should be a little bit less than 5 minutes. Change resolutions 50 times. All right. So, hi everyone. I'm here to talk about what we're up to at Modular. So this is kind of a personal quest, a journey that we're going through. It's pretty exciting. I hope it's interesting, and it touches a lot on GPU programming, among other things. So one of the things that I was lucky to be around was Dave Patterson and this time of this rise of heterogeneous compute. And I've seen a lot of computers be created from CPUs up through all these things. I work on TPUs at Google. And one of the things that he talked about is that there's this amazing golden age of new computer architecture. You look at what's happening with GPUs, TPUs, all this stuff. Dave he gave this talk at his Turning a Word lecture, and it was really impressive. Now the problem with this is that there's no software for this, right? There's all this hardware out there, and everybody's still struggling. And so when I was at Google, I was leading a bunch of the AI infra stuff that I saw, and we had TensorFlow with graphs. We were working with CUDA, of course. TPUs had to create their own thing called XLA, and mobile had a completely different stack. We also had like 7 other chips, right? And one of the things I learned from this is that there's like all these different stacks. Everybody's reinventing the same things, and so one of the projects that came out of this was this MLIR compiler thing that's now public, part of the LLVM. Lots of people use. I got fed up with Google. I didn't get along with the culture, honestly, and I jumped to a startup company. And a startup company building hardware called Sci-Fi. They're building very fancy RISC-V stuff. Super cool, check it out if you're looking for CPU IP. We built an AI product. And the AI product, then you say, okay, cool, we know how to lay down a systolic array, we know how to make all this stuff, we know memory fabrics, awesome. Where's the software? So again, ran straight in the face of, we have all this ability to build hardware, but where is the software? And one of the problems is that there is software out there, but it was never designed to be general. It's always designed for somebody else's thing, so you're looking to repurpose something, particularly if you're a startup, right? And so, being the smart person that I am, cool, what do I do about And so I gave this talk, kind of a duel to Dave's talk, talking about like, well, it's actually a golden age of compilers, and what we need is we need all the software, and people should stop reinventing stuff, and they should standardize things, and guess how well it worked? Not at all, it turns out. And why is this? Well, almost nobody can even build one of these things for one chip, right? The big companies are the ones that are building all this stuff. They want to lock you into their chip or their cloud or their whatever. Right? I love all the MLR people and all the compiler people and all this stuff, but it's super fragmented, super weird, super academic. There's a lot of motion but no progress. And also, this is just like outrageously expensive to solve as a problem. So I got very annoyed by this, and at the right time we decided, let's actually solve this, and that's what really Mojo is about. I'm going to tell you a little bit about what we're doing with this problem. So when we started the company, we said, okay, this is outrageously expensive, this is a big problem. And so this is a slide we use internally, and so we said, let's take this in a 3-step process. So the first thing we did was we said, let's go solve CPUs. Well, why? Well, you need a CPU to feed a GPU. CPUs are more general. CPUs are actually more difficult in some ways than a GPU. Next, go solve GPUs. Obviously, this is a huge problem. Even 2.5 years ago, pre-ChatGPT, GPUs were the thing, right? This is obvious. But we want to make sure to tackle this in the right way. And then once you get these abstractions scaled into here, you can all go tackle all the fun other cool stuff that's happening in the universe and edge and like all that kind of stuff. And so one of the things that's really important about our approach here is that we want to make sure that we're actually validating what we do. And so I'll talk about performance and other things like this. So let me tell you how stupid this idea was. Okay. And so what are we actually trying to do here? Right. We want to beat vendor performance on their own chips. These guys have been at it a long time. They have trillions of dollars, at least in market cap, right? We want to beat usability of all the existing stuff, right? We want all the research quality stuff that the world has been building on top of to graduate and grow up, because everybody wants to build on top of AI Infra. They don't want to always have to deal with it themselves. We want to unlock research. We want, like, for example, Tree's amazing talk, we want all that stuff to go faster, and we want generality so there can be innovation at the hardware level. And so if you look at why this is hard, just on CPUs, well, just within CPUs, you have massive architectural differences across the macro architecture. Even if you pick Intel, you have now massive numbers of different instruction sets, and AMD just added bfloat 16 fancy things, and like you have all this like diversity that you have to deal with. You can't scale. Like you can't just write all the kernels. These are also complicated. You've got SIMD, you've got NUMA architectures, you've got distributed machines, of course. You've got tensor cores, what they call them AMX instructions, and things like this. And this is often like a super mature problem space. People have been working on this for a long time. So let's take a new approach. So one of the first things we did was we built this completely new programming language called Mojo. This is very confusing to people. I think a lot of people don't understand why you would be insane enough to build a programming language. But let's start with what it is. Well, Mojo is a completely new programming language. So this is a new compiler built on MLR, all kinds of fancy technology underneath it, that looks like Python, and so it's a member of the Python family, but it's a systems programming language. This is not the Python that you know, and the systems programming language is really important. Now, making a language successful, you have to build all the tools, and so we've done that. It's freely available, you can go download it, we're open sourcing under Apache license. We have something like 50 patches a month coming in, and we're kind of getting crushed under the interest, but it's all very cool, even just for CPUs. We have a nice community, you can join us on Discord. But what is Mojo? Right? What is this actually about? What we're doing is we're taking the things that I love about Python. And what that is it's the developers, the accessibility, the number of people who know Python. And we're taking the ecosystem of code that already exists, which is all the packages. What we're not taking is we're not taking its implementation. And so what we did is we brought in a whole bunch of next generation programming language, compiler, and other stuff into this, and we're bringing that together. And so what this means is that while it looks like Python, please forget everything that you know about our friend the state. So is it fast? Yes, it's fast. It's depending on what you're doing, it's like 1,000 times faster than Python, which is cool. We work back from the speed of light of the hardware. We do not work forward from the speed of whatever Python is and try to make Python better. And so something that's very controversial but also true is that we're faster than languages like Rust and C++, because we built an entirely new compiler stack that's not the 15-year-old legacy thing that Rust is building on top of. We also learned a lot from all this kind of stuff. And so this, for example, is just one simple example, is just a classical tokenization algorithm the thing that's cool about it is you can just write for loops in normal code and it goes fast, right? And this is actually pretty profound when you're looking at ML systems that are fractured between often C++, Rust, CUDA, and and Python, and all this stuff together. Now, we'll get to AI more in a second, but if you look at AI models, you can download them today. We're something like 6x faster than Llama.cpp at N4 on Intel machines, which is pretty cool. And what that is, that's a combination of not just having a fast programming language, but a lot of the technology that we'll be talking about in a second. And so if you want to try this out, you can go get this. This is actually a pretty big deal because I think Llama.cpp is what really invented N4 and 6 and so on. So I want to talk about GPUs now. So unfortunately, our GPU support's not quite done yet. It's coming out soon. I'll talk about that in more detail, but I'll talk about why our approach is hopefully interesting. Before I do that, let me tell you why it's hard. I think you know a little bit about this. But first of all, from our perspective and from the system's perspective, you have to have things like offload. Like you have a host and an accelerator talking to each other. You have split compilation. We want one program that can talk to all the different parts of this. Now for us, that means split compilation across multiple architectures, which is exciting. You also have even more complexity. You have the asynchrony that Tree was talking about. You have tensor cores. A lot of this is actually similar in spirit to what CPUs have these days too. But also, it's more than just a kernel. Like AI today is like page attention, right? It's these LLM optimizations, the higher level systems. And this is where a lot of the performance unlock comes from. And so, you have to get the kernels right, that's right, but that's not just where the performance comes from. It's a whole system architecture approach. And so what we wanted to do is we want to do all this while maintaining the same programming model and make sure it's consistent across CPUs, because these machines we program are heterogeneous. They're not just GPUs or CPUs. So what we did about this was we created an entirely new AI framework. It's called Max. It's focused on inference. Yes, it talks to PyTorch as well, and so you can do training with PyTorch and things like this. We're building into this. I'm not going to spend a whole lot of time talking about this. I'm going to talk about GPU stuff instead. But what you need to know about Max is as a framework, it brings together all of these best-in-class algorithms, things like XLA or TVM or Onyx Runtime or CUDA or TensorRT-LLM, like all of these systems. It brings it together into a next-generation system that we've built using the experience that we all gained building the first generation, which is kind of damaged and flawed in various ways. So I won't be talking too much to compiler here. And so what we did is we said, okay, well, let's actually go and build a full stack replacement for the modern GPU stack. So this isn't just a replacement for CUDA, C++, or something like this. This is a full stack replacement including driver, programming language, kernels, LLM optimization, and serving to provide the full stack that is now portable and can be used on multiple different architectures. And so one of the things that's cool about the stack is it's very consistent for CPU and GPU, which means that you can get actually I think perhaps the world's first real unified local to cloud development kind of environment, which is really, really quite nice. So let me show you some code. Let's start with the basic stuff. If you write CUDA, then you've seen thread IDs and things like this. One of the nice things about this is in Mojo, you can just go nuts and use everything you already know, but now you're in Python land. It's Mojo land, but it looks like Python. And so this works exactly the same way as CUDA does. Compiles to PTX. You get all of the fancy, powerful features you'd like to use. The thing that's really cool about Mojo versus CUDA C++ is, first of all, it's not C++, which is kind of cool. It's easy to learn. But the other thing is that how should I say this? Can I be mean? SD tuple sucks. There's so much about C++ and STL and templates and compile time and this whole nightmare that we've been living with C++, it's just driving us freaking nuts. And so what Mojo does is it brings this super powerful metaprogramming system, if you're familiar, derived from like Zig and other more recent languages into this world, which enables building these abstractions and doing high level programming. But the basics looks the same. You can do everything you've done before and it's all consistent. Now, when you bring in this power of Mojo and what does it enable you to do? Well, one of the things you can do is you can build fancy abstractions on top. So one of the things that we're inspired by is for example, the Triton language community has done some cool stuff for bringing tile-based programming into the world, and Cutlass, and lots of other people have done this. And so what we did is we said, okay, well, let's actually build this in a Mojo, not as a compiler, but let's just build a library. And so what we allow you to do is do fully async tile-based programming yes, it supports dynamic shapes, yes, it supports TMAs, yes, it supports tensor cores, of course, like that's all kind of table stakes these days. But the cool thing about this is it's simple, predictable, and it gives you the full power of the machine. And so if you're curious how like you can get simple predictability and full power of the machine, it's very compilery, and so we gave a talk at the LLVM meeting in the fall, and you can find out more about that, how that kind of stuff works. But one of the things that's very important about our approach here is we're not trying to put all the magic in the compiler and take it away from kernel authors. What we're trying to do is we're trying to make it so that smart advanced developers can go use the basic features to build, for example, asynchronous memory pipeline, fancy thingies that I conceptually understand, but I'm definitely not an expert at, by the way. And then build these things into libraries and build abstractions into them, and then reuse them. And this is how software has generally worked and scaled, and so what we're doing is we're learning from traditional software and pulling it forward. And then, yes, giving you fancy integration with the graph compiler and staticization and autofusion and all this kind of stuff that then makes it so that you get a richer programming model. One of the cool things about our stack with Max is that being able to write a custom kernel is very important, but being able to not have to write a custom kernel is actually pretty cool. And so we provide a very simple graph-based programming model. When combined with our auto-fusing fancy compiler, means that you just get fused kernels. Now you're not going to get a tree quality fused kernel out of this probably, right? But one of the things that's really nice about this is that this thing, which you can put in the category of like XLA or something like that if you're familiar with this, makes it so you can just write code that looks far more like PyTorch, and you just get pretty decent quality fused kernels out of the box. And what we've seen is that in many cases, this beats like the hand-fused kernels that you get out of CUDA and things like this. And so the combination of a few very fancy kernels combined with graph compiler gives you a lot of power. And the nice thing about this is that you can think about things from a math perspective instead of having to think about all the different implementations, details of this. As I mentioned before, we have a driver, and so we're not just talking about programming language stuff. We actually, to talk to a modern GPU system, you often have many GPUs. Some people want to control things at a very low level, and I believe in giving people full control, and so you can go nuts, and you can create different devices, and you can select kernels, you can copy memory, do all this stuff. One of the nice things about it is that it's architecture agnostic, and so it's very funny, in Python you can open your CPU and submit high performance kernels to your CPU, and now you can offload to the same machine you're on until it works. This is even more powerful in the future when we bring in distributed support, because you want to be able to open a GPU on a different device on a different machine and things like this. So there's nothing like rocket science about this. It's just really nice, it's easy to use, and it's familiar, but it's also portable as well. One of the things that's also really important about getting performance is tools. And so a lot of achieved performance is being able to use things like profilers. A lot of achieved correctness is debuggers. And so Mojo, as like a full tool chain and actual language, one of the opportunities that affords us is we can have like direct integration with CUDA GDB, with Insight Profiler, all this kind of stuff. It all works exactly as you'd expect, and it's completely native. And so this is really important for our team to be able to get high performance on these crazy modern architectures we're all dealing with. So anyway, so what I told you is that we're building a whole bunch of crazy stuff. This is actually really hard, the scope and scale of what we're doing. And so you might ask how much performance you have to give up to be able to get better usability. And so we haven't launched, and we're not ready to talk about everything, but we can show you some examples. We did a study of our matrix multiplication written in Mojo, and by the way, all of our kernels were written in Mojo. We compared against one vendor, which is pretty popular around here, called NVIDIA. Their market cap is a few $1 trillion more than ours, by the way. But one of the cool things is that we're able to already beat CUDA and Cutlass by a little bit. And that's actually pretty profound, because this is head-to-head drag racing on Tensor Core. Like, this happens to be on A100, but this is just like drag racing on fully dynamic, doing the exact same thing. This is not staticizing or cheating or other things like this. This is also not bringing the advantages of kernel fusion and all the other stuff we're talking about. So we'll be talking a lot more about performance later, but it's pretty cool. And TLDR, you don't have to give up performance. In fact, you can get better performance because you can understand what the code does. So let me tell you an open secret about all this stuff. So we're an AI company, modular AI, but none of this really has anything to do with AI, really. this is all about accelerated compute, right? And so the thing that I think about, and the real motivation coming back to the beginning, is that hardware is changing, right? You think about programming today's systems and what a pain in the butt it is. Think about what we'll be in 5 years. There's going to be more hardware, more diversity, more specialization, more craziness, more fancy algorithms burned in silicon, because fundamentally silicon is two-dimensional, and so you're going to get more things like tensor cores that are going to be specialized to the application. So I'll wrap things up. The whole point here is we want to give you superpowers, right? So we are about enabling programmers, we're about giving you cool tools, we don't want to put all the fancy stuff into a compiler, we want to give you the power of fancy compiler tech. If you go check out our webpage now, you can download Max and Mojo and have a lot of fun. There's like LLM things, you can play with PyTorch stuff. The open source community is building things like GUI libraries and serving frameworks and all kinds of stuff, because Mojo is very horizontal and very nice. We have nightly builds you can check out as well. We're launching our NVIDIA support this fall. I'm very, very, very excited about this. I know a lot of other people are as well. Secret for y'all, we're going to be doing a marketing launch late this fall, but this will all be available in our nightlies in like a month-ish. And so we're not going to make a lot of noise about that, but if you're curious about that, please join our Discord. How much does it cost? By the way, it's free. This is not a try to lock you into a thing. Our whole business model is around enterprise support, about building managed services and things like this, and so we do want to let you get a license if you want to go build a managed service and compete with us, but if you're a researcher, if you're playing around, if you're building your own stuff, if you're a massive AI research company or whatever, like, go have fun, that's cool. So imagine a world where you can have innovation unlocked in hardware. We don't have to force people to learn Python, C++, CUDA, Rust, like all these things. We can have unification. We can expand and close this. We can close this gap between research and production. We can have more AI in our lives. If you're interested, please check us out. We're on the web. Also, we're hiring a ton of systems people, and if you're interested in high-performance GPUs and end-to-end performance and LLM optimizations, any of this kind of stuff, then it's a really exciting time. So that's it.
Question?
Is there support for Jupyter notebooks?
Yeah, we totally support Jupyter notebooks, for sure.
With compilation or interpreted?
That's a complicated question because we use JIT compilers. Yeah, we have a lot of compiler stuff, but I didn't even touch into it. But yeah.
So in the example that you showed, there was like exploit ID.x, exploit ID.x. So you mentioned that like, there's no difference between like CPU programming and GPU programming, but what if you like run the same program on CPU?
Yeah.
What would those?
Great question. We're not trying to make different architectures be the same. We're trying to remove unnecessary differences. And so if you have a tensor core, like you need to be able to reason about a tensor core. Like you need to be able to reason about the architecture. But on the other hand, if you need to overload an operator, you don't have to learn a new way to overload an operator. Just use dundrat. And so what we're doing is we're like the cloud-based programming model works on CPUs and GPUs, but the architectural differences are things that kernel experts need to own. And so we're not trying to erase that.
So you know, there's like that XKCD about how like, oh, there's too many standards. Like we need to create a standard that like unifies everything, and then it's like there's another standard. I'm curious like what design principles you're trying to put into this effort to like prevent that,
Yeah.
or just how you're thinking of it, given you've literally built like a lot of the ecosystem already.
Yeah. So I don't know what other standards you're referring to. You're referring to PyTorch, Sickle, like One API.
Yeah, I guess I look at the Max, like the framework where it's like we're building our whole stack like all the way down, and it's like how do you prevent it from being like another stack on top of it? Like what I'm curious, like what if there's a takeaway principle that you are like anchoring to when you're building all this out.
Excellent question. So I'll tell you what we're doing. I can't tell you that we're right. What we're doing is we're learning from the past. So take One API or Sickle or things like this. They're all based on OpenCL that like Raja and I and other people worked on in like 2007. Right? The world has changed fundamentally. Like you need tensor core first programming models and things like this. And so learning from all that kind of stuff and being able to move forward and reinvent what makes sense, I think is very important. If you're looking at PyTorch, well, PyTorch is struggling with GenAI. GenAI fundamentally changed the game because it's not about a graph anymore, right? It's about fancy optimizations where you're utilizing many GPUs. Like you're doing you're like a lot of the things that made sense back in the TensorFlow days or things like this,
Yeah.
they don't translate forwarding, and so a lot of the assumptions that these systems were built on top of break.
Right.
Now, will this thing be a mess like the last ones? Well, probably
But there's
a
like a
little
set
bit.
of assumptions that you're encoding in it of like, it's,
Yeah, what we're doing is we're just learning from this. Like, I mean, TensorFlow, PyTorch, JAX all date back to 2015, like 2016, and so a lot has changed in the industry since then. Yeah, Fish.
I don't remember if I've asked you before, but there is like the scalable vector extensions, which is the kind of CMD instructions of variable length. Do you already support those within Mojo, and what's your way of thinking about them?
Yeah, so when I was at Sci5 doing RISC-V, they
Mhm.
also have their thing like SVE, but for RISC-V. There are good things about it, but massively overplayed in terms of hardware abstraction.
Mhm.
So for those who don't know what variable length vectors are, the idea is that you could write, for example, a dot product and write it in a generic way so that it can adapt to future generations of hardware that change the architected vector. That's dumb, because when you start doing, for example, a matmul, you have to know how big your cache is, right? And so the good thing about those ISA features is they make it so you don't have to re-encode your entire instruction set every time you want to change the vector length. But you still need fancy compilers and architectures and kernels that can make you adapt when all the parameters of your architecture change. And so what we do is we say, okay, yes, you can access that, and you can talk to anything that LLVM or MLIR, and like our stack can talk to anything. In principle, we haven't implemented everything, of course. But it doesn't solve you from having to solve these. It doesn't prevent you from having to solve these problems. Now, I didn't talk about it in Mojo, but in Mojo, it has this very fancy parametric metaprogramming system, and so by default, it encourages you to write generic algorithms. One trivial example, which I know you'll like, is that we don't have scalar and SIMD types. Scalars are just a SIMD of one. Right, and so if you're writing sine and cosine, of course you write it to be generic on your vector length, right? And things like this. And so there's a lot of very simple things like that that go a long way.
Very cool.
How does it work on Apple devices that use Metal? And do you see yourself as competitive with that? I guess sort of more global question, for all of the existing CUDA competitors, why has CUDA managed to beat them out for the most part?
Okay, so let's separate these questions.
Two
So,
different questions.
yeah, so we are coming out of CPU land, we're doing NVIDIA. And NVIDIA is really important to us, they're a great partner, and they have really cool stuff going on, of course. So we haven't done Apple GPUs.
I see.
We've talked about it. His team says it'll take 3 weeks to do or something. But we have not done that. Oh yeah, Mustafa leads the GPU group and a bunch of other stuff.
I see.
Yes, and so he's also a lead CUDA hacker. He led CUDA back in the day and
3 weeks to
things of that. So my problem is I have to keep people focused. And building the world's best GPU programming model that exceeds what people are used to with CUDA is really hard. Okay, and so I want to make sure that we do something that's really meaningful and it's a contribution to people that are actually programming GPUs, not being another thing that's like a demo that only works in special case. And I like building production stuff, and so we'll expand out when it makes sense to do that. And Apple GPUs are very interesting, most notably because local to cloud, and lots of people are using Apple laptops, and so I really love that community for lots of reasons. And so I suspect we'll do it at some point, but we haven't done that yet.
And the second question.
Oh yeah, sorry, what was the second?
So why has CUDA been so reliably dominant, and how do you frame?
The way I would say that is, so I think there's many factors that go into CUDA being dominant or successful. One of which is that it was ahead of its time and executed well. The other is they kept compatibility. And a lot of the other people, every 3 or 4 years, they'd lose focus and try to do a new thing, and they would just fragment their internal stack, and they would, I'm not going to name names, you know all the other names, right? But, they just turned into a software nightmare, even within their own walls. And trying to unify FPGA programming into GPU programming is a little bit of a fool's errand.
So we shouldn't expect Mojo to ever get compatibility.
Well, so that's a little bit of a different thing. I was talking about hardware compatibility, right? And so other people, for example, had different software lines on, for example, laptops versus data center and things like this. So, but again, there's a lot that goes into that. CUDA is also really well executed. Also, the hardware is really good. Right? I mean, there's many different factors that go into success.
Last question.
Yeah, similar along the lines of the question about the thread IDX on the CPU. Could you compile the SIMT programming model to SIMD on a CPU, so could you program a CPU using the same kind of model?
Let's talk later. All right. Don't have anything to say about that right now.
Thank you, Scott. So briefly about Dylan from SemiAnalysis. So he's been publishing all sorts of very edgy, some of the controversial, very technical arguments about whether OpenAI is doomed, about whether, about exactly who they're poaching, and whether it means that they're serious about creating their chip or not. Looking forward to hearing a few words of wisdom from the founder of SemiAnalysis.
Just Dylan, why CUDA has been so successful.
I think you'll like the first meme then, Chris, because it's kind of Rohan asked me a few days ago to present, and I was like, oh yeah, I threw something together like 20 minutes ago. But this meme I saw on Twitter today, or yesterday, it was really good because it encapsulates how ridiculous programming GPUs is. Half of these I had to look up myself because I'm not actually that great at it. But the one thing I did know is it didn't call out Cutlass. But yeah, there's a ton of crazy complexity when you're trying to program a GPU really quickly. It's like check out Cutlass, check out the YouTube video that's linked there that's on CUDA mode. Other thing I was just going to talk about was a bunch of GPU data centers because I thought that was cool. I was like, yeah, let's talk about them. Right, so this is in Arizona near the airport. Each of these buildings is 48 megawatts, and sort of when you build a data center, you kind of design something and then you stamp it everywhere, right? So Microsoft has over 100 of these data centers across the U.S. Each of these rectangular buildings. But when you think about, hey, well, what do you do if you're OpenAI and you've already trained GPT-4 on 20,000 plus GPUs, right? Well, the next step is 100,000 GPUs, obviously. So what exactly does that involve, right? So there's these 3 buildings. Each of these buildings has 32,000 GPUs in it. It's a ton of money. There's all this stuff about networking that I won't get into. But the interesting thing is if you're OpenAI and you think that raising $7 trillion is actually a reasonable thing to do, what is the next thing you do, right? Is you build this data center that is not 100,000 GPUs, it's 175,000 plus of the next generation GPUs, right? And again, this is hundreds and hundreds of megawatts, extremely large. And if you're OpenAI and you have problems with Microsoft being slow at building things, what do? You also go to Oracle and you tell them to build you 100,000 clusters of GB200s as well. And then they have many more data centers all across the US and other places that they're trying to build. And so I just thought that was interesting. You got to think about the dollars and cents here, right? Anyone who works on CUDA, right? I said it was super complicated. I couldn't even explain that meme to you. I think there's maybe 5 people in the room that can explain every single item in that meme from the beginning in this room. I think Pradeep is probably one, but I don't know. Maybe Tree is probably another one, but I don't know who else could. But the interesting thing here is these data centers, right? That Oracle one that I showed you, it's $12 billion that OpenAI is going to pay Oracle over 4 or 5 years, right? Think about what does 1% efficiency mean then, right? If you think about, hey, NVIDIA shipping 5 million GPUs a year, right? This year, data center GPUs, H100s, and then early Blackwell, you have, hey, Tree just increased the efficiency by 10% of every GPU in the world. That's $8 billion plus, right? Tree is a G, right? And he gave it away for free. So that's really the motivation here is all I'm trying to say is really be more efficient because that's a lot of money and a lot of power that's just being burned uselessly if you're not efficient. Also, just throwing in some other slides, Elon's crazy. He's building 50,000 GPUs in a factory. He's also extremely crazy in terms of buying an old factory in Tennessee and converting it into a data center. None of these data centers are green, even though people tell you they're green, because wind power renewable is like this, and solar's like this. It's all gas powered, right? All of them. Don't let them lie to you. They'll buy these things called PPUs. Which are basically you buy power from a renewable site, but then the power is not necessarily what's feeding your data center, and you can claim that you're green, but you're actually not, right? A lot of the power is is wind, but or solar, but that does stop, and so you have to have gas as a backup. So your efficiency is also about saving the world from not burning, right? And I think it's yeah. So you have people going crazy, building 100,000 clusters everywhere. These are just XA and OpenAI. I won't talk too much about the networking stuff. I think that's like sort of like in the topology and all that. But another thing is like, hey, if you can get data centers across the world to work together, at least data centers in the same state or region. Jeff Dean claims he's figured a lot of stuff out here. Well, at MLSys, the conference, he claimed that they'd figured out a lot of stuff. And if you do, then that means that you don't need to build another 100,000 GPU cluster. You can just like connect your old ones together, right? Maybe. But the real thing that that I've been working on recently, just like for education purposes, really, is all reduced, right? So Llama 70B is like 80 layers, right? And there's multiple all reduces in each layer. So when you think about it, there's like, if you want to do 30 tokens per second, there's like 5,000 communications you have to do between the GPUs every second. And when you look to Llama 405B, it's releasing on like July 20-something. So really soon. It's 400 billion parameters, right? 405, 410. It can't fit on a single GPU. You need the whole node, right? So you need all 8 GPUs. How do you have these communications within the layers without murdering your inference rate performance, right? And if you want to have achieved 30 tokens per second, it's over 100 layers. It's like almost 10,000 communications you have to do between the GPUs. So what I've been trying to learn or do, there's libraries already, but I've been trying to figure out how to do different techniques and profile them. So I'm not going to use the gracious GPU that someone provided because I kind of need more than one today. But I also found a random place where, not random, this is a Singaporean company, where they stick the entire server in a vat of liquid that's made out of hydrocarbons, and that's how they cool it. That was pretty cool. And then like this is some early performance, right? Trying different things out, NVLS, ring, tree, right? These are all different ways to do the all reduce, right? Whether you go from one, you go in a ring around all 8 GPUs, so there's 8 or 7 communications, or 8, yeah, and then you broadcast it all. Then, or if there's a tree, so people aggregate up, or if you do all to all. So I'm working on doing the all to all now. And then the reason this is really important is because the unit of sort of compute is not an H100 node in the future, right? That's what it is going to be for Llama 405B, one server. You have to figure that out. But the next thing that's happening is the GB200 rack, and NVIDIA is going to ship. Majority of their shipments next year will be this rack format. So that means you need to now figure out how to make 72 GPUs communicate over NVLink and schedule the communications, and not just use NVIDIA's crappy nickel because it's really poor. That's really about it. I just didn't have a rhyme or reason, but that's what I'm gonna be working on. Yeah.
Any questions for Dylan?
Yeah. So where do you actually go to like learn all this stuff? Like I started thinking Substack like 3 days ago, and I'm like, holy crap, this guy like knows everything.
So like those satellite photos. We take satellite photos of over 4,000 data centers every month because we want to know like when they're building the production. And then we sell that data, right? Like energy traders want to know. There's like a client of ours who bought a natural gas facility in Dallas because like there's a lot of data centers being built here based on your data, right? Like there's all sorts of random stuff. So you got to do primary research. You got to do primary research because there's no like online stuff. Semiconductor industry is like horrible because no one posts anything on the internet. Which is also why if you ask LLMs about semiconductors, they get a lot of stuff wrong. Like the papers in IEEE and stuff are like way too like deep, and then like the books are all like over here. So how do you learn about semiconductors is really like, for fun, I would say just go to Asianometry's YouTube channel. But if you want to actually like work on it, there's a massive leap of like stuff you got to do, right? So like the specific data centers I'm showing you is mostly because of like, we're looking at the data centers being built. But as far as like how everything works, I think John's channel, Asianometry, is probably the best place. There's a construction physics video on YouTube that tells you how semiconductors are made. Those are more like, for level 1 through 10 to like whatever level.
What do you mean you take photos of
satellite photos, right? So Airbus and many companies have satellites, but you can just like contract them to take photos. So in the past, like energy traders would often like look at like oil platforms to see if they were flaring off or not, to see, then they could project like earnings. And like one of the guys on my team used to be an energy guy, like trader. So they were like, oh, it's this with data centers. And it's actually like, there's a lot of useful information you can extract. But yeah, you have to pay like hundreds or thousands of dollars per photo. So it's pretty crazy.
You may see Dylan detained.
I have not taken any photos of Chinese data centers yet, but I plan to.
You will come back.
You showed a data center, I think, with like submerged mineral oil cooling in Singapore. That's pretty hard to scale. How?
Yeah, I don't think it'll work. I don't think it'll work because like it's cool because it's like and actually in Kuwait there's a prince that's extremely rich who like somehow someone baited him into like this mineral oil is made out of oil, so you should like invest heavily in data centers. And cool this thing. It's not scalable as Ash was saying. There's a lot of challenges with using, dunking hardware in oil when hardware is unreliable. To take it out, you have to wait for the oil to like not get in the wrong places and fix stuff. So no, people are just gonna do like water cooling and air cooling. But I thought it was just fun to point that out that exists.
Lastly.
What happened to all the infra for blockchain and Bitcoin mining? Is it transferring over to?
Yeah, so there's a lot, right? So like I personally invested in a North Dakota facility that's converting from crypto to AI because I think we can sell it for a lot. But like there's a lot of data centers like CoreWeave. They've contracted like Core Scientific and got like a few hundred megawatts, right? A few hundred megawatts is a few hundred GPUs. Converting those from crypto data centers to AI data centers. So there's a lot. There's globally like 15 gigawatts of crypto data center capacity, which is ridiculous. Does nothing. We can talk after.
I'm pleased to give you Raja Koduri. He's been at AMD, has done phenomenal work at Intel, and will give us the real answers to why CUDA has been so successful through a whiteboard talk.
If you want to, I can help you move it a little bit.
Yeah. I didn't want to topple a bunch of things. I was designing or being involved with designing the GPUs since probably most people in this room were even born. That's not a like a bragging statement. It's kind of like, I think I earned my credentials, or I can do some dad jokes on CUDA. And you should laugh. So that beyond that. What I wanted to do, since just 10 minutes in this stuff, I can talk for 10 hours on the history of GPUs and why kind of CUDA and NVIDIA won. Because since 1995, every 5 years or so, right, there is this cycle we went through where, this is it. This is the end of GPU. This is done. You guys just go do something else, go find another jobs, right? We went through these cycles. And even most recent one was when Google announced the TPU in 2016. You can go and check kind of, NVIDIA stock dropping and all that stuff, saying, TPU and, the famous Patterson speech on domain-specific hardware and all this inefficient things will die, and there'll be a domain-specific language for AI, and it will win and all. And it made sense to all of us, including, even though it was not very good for me being on the GPU side. It made technical sense what smart people were talking, but it didn't happen, right? It didn't happen. So I left my kind of big corporate jobs and all about 15 months ago, and just spend time connecting the dots backwards, right? What happened over the past 25 years in this stuff. And So I put the connecting the dots down in a simple set of mathematical equations for you to kind of walk through, right? So, and this applies not just for kind of GPUs, as someone said earlier, I was talking, it also applies for why CPUs won. People said the same thing about CPUs, that when at the beginning of the internet era, they said there'll be this special network accelerators, Java accelerators, and all these things that are going to take over, and ARM x86 thing is limited. And here we are in 2024. We're still using x86 CPUs, ARM CPUs, and now there's 5 CPUs. So I call my AI equation is I say AI, okay, but the A and I stand for something else. In my world, A is architecture, and I is impact. Right. So the impact of any architecture, you can apply to CPU, GPU, has been, I do use the multiplication equation, but it's a function of performance times generality. Right. So you can actually kind of walk through the history of things and why things won with just this simple equation, performance times generality. Okay. So today CPUs are very general. They're the most general, right? And that's why Chris started on CPUs to get Mojo going on that stuff, right? But their performance, when it comes to graphics and AI workloads, is not adequate. So on this equation, they lose. Even though their generality score would be higher, their performance score would be way low. And if you take some of the dedicated AI ASIC hardware, their performance score on dedicated models would be high, but their generality score would be very low. And the right balance right now is achieved by GPUs, and more specifically NVIDIA GPUs. Okay? So on this equation, they have the best score. You can mathematically go across a whole bunch of workloads and a whole bunch of stuff, and that's why they are $1 trillion company, because they have the highest score on this particular thing. And the second thing is, in the history of parallel programming, and this is actually a challenge for Chris and everybody else as well, there hasn't been a successful architecture whose programming model was different than the execution model of the machine. And this was a statement I read in 2006 in some data parallel programming handbook, or by some a French mathematician who was doing HPC for a while. I didn't understand back then. I understand now. I understood it about 10 years ago. But this is one of the core reasons: the CUDA programming model and the GPU execution model. How when you look at CUDA code, how you arrange your thread blocks, your groups, your your scratch pads, your stuff, and how a H100 SM executes or an A100 SM executes. You can see one-to-one correspondence between those things. Yeah, you can call it low level, it's ugly, it is this, it is that, and all, but the execution model and the programming model match. And why is this important? Okay, because see, if you didn't care about performance, you wouldn't even be talking about CUDA, right? You wouldn't be forget CUDA, you wouldn't be talking about parallelizing an algorithm, right? You write an algorithm sequentially. Our prefrontal cortex thinks sequentially. We we learn math, we convert math to programs. The reason you're going and doing that extra work of parallelizing something is because you care about performance. So after you did all the work, if you don't get the performance, you'll be disappointed. Right? So you don't really like putting all that effort parallelizing stuff, right? And not get performance. And that's one of my experiences of, we've done many, successful, unsuccessful, mostly unsuccessful parallel programming efforts, right? Saying productivity is more important. But productivity is not just developer productivity writing code. Productivity is how fast you can achieve performance. Okay, so how do you define generality? Right, so generality is a function of, Chris mentioned this compatibility. See, he's hitting these things, right? Is it compatible with existing models? existing programming languages, which are C, C++, now Python, and unfortunately CUDA. Okay, in the stuff, unfortunately in the stuff. You have to be, whatever new thing you do, you have to kind of think about compatibility with these things. Now, at the dawn of CUDA, okay, the GPU architecture prior to that, right, was focused on graphics, rendering. We started with triangles, pixels, then we introduced programmable shaders, right, and once we introduced floating point computation into the GPU, like, just opportunities opened up. But it wasn't compatible with the most important programming language of the time, which was C, C++, right? So CUDA was the first, and what is the fundamental attribute? Once we got programmable shaders, floating point stuff, there's one important element missing on the GPU to make it compatible with C, C++, which is pointers, okay? Pointers, right? Load store with pointers was the biggest kind of leap. CUDA was the first language where pointers support was added. So you could do all kinds of C, C++ based things into that stuff. So it bridged the gap between the GPU shading languages and kind of the CPU world a bit. But it's still very different world, right, to extract performance and all that stuff. So, the pointers is a much underappreciated thing, not just for programming reasons, but also how you integrate a GPU into the rest of the system software stack, Linux drivers and all that stuff. And this is a very often repeated mistakes I saw in all the 20 or so AI hardware companies that are around here in the Bay Area and elsewhere, right? Actually, none of them I talk about pointers. Why do you care about pointers? We have a tensor things in there, right? PyTorch. Everybody's programming in PyTorch. We don't see a pointer in Python, PyTorch. Where you care about pointers? But if you double click on the PyTorch code, the first thing it does when you do, right, whatever A equals to tensor something, it calls a malloc. Okay? And then, all hell breaks loose by the time it gets to the device, right? They're just working backwards on a whole bunch of stuff, right? yeah. So compatibility. The second stuff, that's not enough. You need to be extensible, right? People need to be creating new languages, new libraries, new stuff, right, on top of whatever your programming interface. And last but not least, this is a huge advantage for NVIDIA, is accessibility, okay? And people think that all GPU programming is on the cloud, and you have cloud GPUs and H100s and all. You just should get out and go to places like India or China and other places. Cloud GPU is not a common thing. It is only for those of us who are very rich on the west coast of America. They program on a 3060, $299 GPU. Okay? Gaming GPUs are everywhere. Every corner PC shop has a gaming GPU. They start over there. Okay? So accessibility is very important. Now, so that's the generality equation. Now, this is the most interesting equation, is performance, right? The talk, we heard from Trey and Chris, right? So the performance equation, by the way, interestingly, the GPU performance equation and the AI performance equation, I have a sigma, right? It is a function of flops, bandwidth, let me just say bandwidth, and interestingly, capacity, this is the memory capacity, divided by power times cost, right? I know most of these people here may not care about power and cost, but the infrastructure that Dylan was talking about and all, and the ridiculous cost of that, right? The work you do as you build all your stuff, if they have to reach 7 billion people in the world, these two, power and cost, need to come down dramatically. You can, 1 megawatt now costs $30 to $40 million to build, okay? That needs to come down to, less than $10 million, less than $5 million for it to reach the internet scale. AI to reach internet scale, these things need to come down. Now, if you look at F of flops, bandwidth, and capacity, so when we did the programming, first programmable shader GPUs, the ratio of flops to bandwidth was 1:1. Okay, for every flop per second, we had 1 byte per second. Now, if you look at a H100 on just bfloat 16, that number is 350 to 1. So you have 350 flops for every byte that you fit. So like all your optimizations, you can break down trees optimization stuff on basically how do I utilize those flops more efficiently. That's why the bytes, the memory optimizations are very, very important. Now that ratio changes depending on which level of cache hierarchy you're looking at. I'm talking 350 is to the HBM. Now it will be half that for their L2 cache, or maybe quarter to that to their L2 cache. And to the L1 cache, it is another quarter. And to the register file, another quarter. So you can bring that ratio from 350 to 1 to 10 to 1 if you keep the data, if you're reusing the data that is very, very close to the SAM. So most of the optimization stuff is kind of, is surrounding this equation, right? It's actually, from the matrix math that Tree showed, my advice to everybody looking at optimization is don't even go to profilers and all first. It'll confuse you. Just take that math and compute the number of mathematical operations there are, right? You can just kind of compute by hand or in a spreadsheet and divide that by the flops that are on the machine and the bytes and the stuff and say how far are you from the theoretical peak, okay? That will just start guiding you in your stuff. So a simple, we call those speed of light models, right? And do a speed of light model and you can get to kind of, the root on the stuff. So anyway, this is, I can talk for hours on this equation, further breaking down the power, the cost, and where things are going. But memory bandwidth, memory capacity, and compute and memory coming together is the next kind of, the next 5 years, next 10 years, the next GPU architecture will be based on optimizing this equation. We already see H100 to B200, right? Some of the elements of optimizing this equation by getting two big dash together. So questions?
Question for Adam.
Do you think that multi-core SIMD CPU architectures will ever be able to match the throughput of stream processing type GPU architectures, or is there fundamentally just the stream processors are more efficient and better?
Yeah, so the best way to think, I use the transportation analogy, okay, for all of this stuff. I think of cars, buses, trains, all take you from point A to point B, right? But if you have 1,000 people, okay, want to go from point A to point B, if you bring them all to a train station and load them, that's far more efficient. So GPUs, modern GPUs with TensorFlow are more like trains, okay? CPUs are like cars, right? They are effective. 4 people are coming from San Jose to San Francisco, but they get you to the final stop. Now, can I add a trailer to it, right? And say I add 10 more or make a minivan and all that stuff. We have done all that, but CPUs fundamentally run on a different infrastructure, right? And there are physics limits of that infrastructure. Now, if you change the infrastructure and say, yeah, you can call them whatever you want, then they become GPUs, and they have the similar kind of constraints as a GPU instruction. So there is no, it's a zero-sum game between the amount of batching of work that I want to do, right? So that's why the cars, buses, trains analogy is a good way for you to think about even achieving, GPU optimization. And sometimes when you have a workload that looks like a car workload, actually just do it on the CPU. Don't spend ages trying to map it to CUDA and this and that and all that stuff. It's actually going to be negative, right? And the stuff. So there is a perfectly capable CPU sitting right there, right? That's accessible to you. So use it for the workload that it is good for.
So I was talking to some startups who are building hardware, and their prediction is that we cannot solve the power and the bandwidth problem. So the future will be a lot of low power cores in the future, as opposed to these very high performance cores, because these challenges of power and throughput are not surmountable. Do you think that's true?
See, the thing is, there is picojoules for flop, that is for compute, and picojoules for bit. picojoules per flop, we are all kind of limited by Moore's law. Okay, there is no magic. If anybody tells you there is any magic, I want to go see them and fall on their feet and so all optimization opportunity now is on picojoules per bit. There is at least 10x optimization opportunity on picojoules per bit on moving data and all. So that's where I think productive things are going to come. On flop, only magic like, oh, can I do 1-bit neural nets? Awesome. If you can, do everything in 1 bit or 0 bits, right? You'll be magical stuff. But other than that, there's, we are bound by Moore's law. Whatever TSMC gives us, that's the, the energy efficiency that we get. Thank you.
Robert Dory. Thank you. Now we give you Ash Vardanian. So Ash is the brilliant founder of Unum, a life project in which he's created a faster vector search service than any I know. He's going to give a great talk about the future of his organization. Ash also is the originator of the Hardcore Hackathon. So at AGI House, we have a lot of these different threads, AI for Thought, the Hardcore Hackathon, and he's been core to making this exist. So thank him for your existence and for your attention. Ash.
Oh, thank you. It will be really hard to follow those 4 perfect talks before this one, but I actually couldn't have asked for a better segue. So the first equation that Raja was showing was about performance and generality. I will talk a little bit about performance at start and more about generality at the end. So yeah, I maintained and implemented several libraries that are open source. They do all kinds of bit swizzling hacks, or bit twiddling hacks, call them whatever you want, where you kind of shift data in different ways, interleave it, and then you can kind of, in a single CPU iteration, can process multiple entries of data at once, which many people know as SIMD or SWAR, SIMD within the register. And we did it for strings, and we beat the assembly of libc by a factor of 3. We did a lot of things for vector operations, but that's kind of boring at CPU side. On the GPU side, however, I think I started programming GPUs around 2009 or 10, and that was on somewhat mobile devices or smaller GPUs. And there's this sample code that I use for demonstrations and teaching for the last 5 to 10 years, where we show how different it is to program parallel reductions on different kinds of hardware, with different kinds of compilers, with different kinds of languages. And sadly, this is practically the only piece of CUDA-related software on my GitHub. And today we're going to change it. So in reality, my team and I, we've been working on a lot of very general applications of parallel hardware. One of which, about 3 years ago, we published our database engine, which is a transactional database engine that can run on a GPU. We outperformed on the CPU side the existing state-of-the-art by a factor of 10, because we like low-level programming, we don't like memory allocations, and we love assembly. But on the GPU, it was even more impressive than that. We haven't had the chance to open source it yet, but I was thinking what I can do today, maybe something more digestible than an entire database engine. And there are all those non-trivial topics that exist around CUDA that most people don't really access. So yeah, we know about those shared memory buffers, or being able to use GPU caches more effectively. But there are tricks that became more popular in the last couple of years that I would love people using today. And I wanted to enumerate some of those so that you all know where to look and what kind of documentation to search for during the day. One of those things is about low-level programming. And I realized it would be too ambitious to give a talk about PTX and SAS in a matter of 10, 20 minutes. But those are the intermediate representations in case of PTX and the low-level assembly that goes onto the GPU. You can program this directly. You don't always have to write CUDA. You don't have to come from the C++ land. Then there is a website that is among my tabs. So when I start my computer, this is the first thing I see. So I get 3 or 4 tabs that pop up. One of them is the intrinsics for x86, the SIMD intrinsics. The other one is for ARM. And the one that kind of everyone neglects, so ARM is not very popular, but CUDA is forgotten by everyone. So a lot of the logic in the GPU land, especially on NVIDIA, operates at the level of 32-bit words. but not all of the data is born 32-bit wide. So if you're dealing with FP8 or int8 representations, there are intrinsics in CUDA that you can use to access more flops per volume of data fetched, or actually I should say more flops per round of data fetching, which is probably more important here. Another thing that became popular a couple of years ago, and this is probably the most messy part of CUDA, it's cooperative groups. So CUDA has at least 3 mechanisms for scheduling. One of them is streams, the probably original one. The second one is the computational graph, or like the DAG. And the third one is cooperative groups. All of them achieve somewhat different goals, but they have kind of interleaving functionality. So if you kind of draw a Venn diagram, there's like a centerpiece where every one of them appears. Cooperative groups are arguably the most functional of those. And they also go beyond like single GPU. They allow you to schedule sometimes like multi-GPU workloads. But then the part that everyone forgets about is this, GPU direct storage. So to make GPUs more widely accessible, NVIDIA actually designed a set of additional tooling for you to be able to map persistent memory like memory from your NVMe SSD onto VRAM, which is an amazing way for you to bypass the CPU and send data directly into the GPU. So if you can work with volumes of data that are, let's say, under 80 gigabytes on the GPUs that we have today, you should look into this. Then, probably the last and the most forgotten piece of NVIDIA's ecosystem is their Rapids libraries. So Rapids, I would say, is one of the highest quality in terms of compatibility with existing Python tooling library or like set of libraries that I've ever seen. So I think I've been mentioning them over like 3 or 4 years now at different conferences. They include CuPy, which is a GPU alternative to NumPy. There is cuGraph, which is the GPU alternative to NetworkX. And there is cuDF, which is the GPU alternative to Pandas. And like, I think Pandas API is like over 100 functions. I think there's only like 2 functions that don't have full argument level compatibility with Pandas. So this is really hard to get done at this level of compatibility, and almost always across the board to get boosted performance. But the reason this matters at the CUDA hackathon is that aside from ability to write just like Python code and have it executed on the GPU using the underlying CUDA frameworks, it also includes a lot of custom stuff for you to write JIT compiled code. So this is the snippet I think I should show you, where you can essentially write heterogeneous code with extern C and then like a CUDA kernel within your Python file. And when you're prototyping new GPU code, this functionality is exceptionally handy. So you can start with the Python code, and then what I generally do, I switch to Numba, which is a Clang-based Python project, and Clang is based on Clang, and Clang is a front end for LLVM. So you get all of this machinery that you can already use today to first design kernels in Python, then JIT compile them on the CPU side, and then use CuPy with the all underlying NVCC and NVC++ machinery to do the same on the GPU. And, well, you could have thought that I'm just talking here, but a couple of days ago, I decided to put my money where my mouth is, or more importantly, my time where my mouth is. So I decided to start like a very small project that can be a scratchpad for all of you. And I thought a catchy title would be Scaling Democracy with GPUs and algebraic graph theory. And what I mean by this, there's a lot of people in the Bay Area who use GPUs to scale matrix multiplications. And we all know linear algebra just works fine on GPUs. But what about all the combinatorial problems, such as voting mechanisms? And I've worked on a lot of those, especially like with the applications to graph theory and the applications of graph theory to something else. And there is an algorithm that is called the Schulze voting method, which kind of resembles the Floyd-Warshall algorithm for widest paths. And it has a structure that is similar to matrix multiplication, but has a sequential dependency in it. So over the last couple of days, I've implemented the Python version, the Numba version, and the CUDA version that still contains a bug in it. Frankly speaking, I could have titled this talk not the Scaling Democracy, but Scaling Piracy. The reason I could have done it is because Schulze method is used for voting within all kinds of pirate parties, and maybe Wikimedia Foundation, maybe Linux Foundation, I'm not sure. But I thought I'm not really planning to testify in front of Congress this year, so scaling piracy was not really on the radar. I decided to go with scaling democracy. Today, I will be fixing some bugs in this implementation and maybe working on other combinatorial problems. But I already went ahead and before we started today with friends from Nebius, I connected to the H100 machines that they are providing. I tested just the raw throughput of the system, and we've kind of proven that there is validity to this. So if you remove the sequential dependency from the algorithm, you can go from 20 CPU cores that is roughly 66 seconds to 3.6 seconds already on an H100. So this is not like pure 20x improvement in efficiency, because 20 cores is not comparable to an H100, but maybe like a 2x efficiency improvement in energy consumption or so, which is a good start. And the reason I'm emphasizing this project is because when you deal with CUDA, probably one of the first things you have to check out is CMake, which is one of my most hated things in universe. I've been writing C, C++ for 20 years. I don't know how to write CMake. So to avoid this, as you see, this project contains no CMake at all. Yeah. Thank you. I suffered for hours yesterday to avoid this. So there is one Git submodule. There is no other form of dependency management of package managers. That connects TCCL, which is the bundle project of NVIDIA now for Thrust, Cobb, and their STL library. So as long as you just pull Git submodule, it works. Then you just pip install locally, and the setup py contains all the scripts to build up the CUDA kernels. It brings up the includes for all the header-only libraries that CUDA has. And there's also a benchmark in Python that compares Numba to the raw kernels. So that's it. If you need a starting point for today's project, feel free to check this out. I'm open to questions, and then we'll give the mic to the Nebius team. Thank you.
One question for Ed.
Can we get a list of those links? This is a good starting point.
Oh yeah, so if you just go to Vardanian/scaling democracy, which probably could be a good title if I run for elections or something, you will find whatever you need to get started.
You can also drop those links in the Slack.
Oh yeah, I can. I will. Perfect. Thank you guys.
Yeah, thank you.
So Nebius is our sponsor for the event, and we'll be hooking all of you up with a GPU with which you can implement your CUDA hacks. So let's hear it for Leonid.
We'll go with PowerPoint. Yeah, so since lots of you are going to use our GPUs today, we thought it would be appropriate to say a couple of words about ourselves. We are an AI-centric cloud, which means basically that you can do all kinds of stuff, all parts of the machine learning pipeline, starting with data processing, pre-training, training, inferencing, fine-tuning. Just a couple of highlights. I won't bother you with commercial stuff. Yeah, as I already said, the full stack cloud with a focus on resilience. Speaking of data centers, we have one in Finland, which is our own data center. Even though Dylan said that there are no green data centers, this one is good. There are a few data centers that just, when Dylan said that, I just remembered that there are a few data centers that heats the nearby town of Mansala in Finland, which we are very proud of, and we are engineering it by ourselves and continue the work still. Also, we are we develop in-house servers and racks. So the data center is, well, proprietary, but the own technology, which we are very proud of. 24/7 support with our wonderful cloud architect team involved, of course. In terms of what you gonna get in the cloud, yeah, H100 of course, L40S, V100, H200 is coming. If you're interested, I'm not sure why you should be interested, but still. And B100 is also coming. We will be one of the first providers to have it. InfiniBand is there. With the help of our own, as I said, we have an R&D team for hardware, but we also have an LLM R&D team. We will develop large language models ourselves. Won't get very deep on that, but still. And so the guys, before even the first clients came, helped us and the cloud architect team a lot in extracting these 3.2 terabits from our InfiniBand. Yeah, and technology-wise, there are maybe some technologies that ring a bell for you. Slurm is there, of course, Kubernetes is there, and some other stuff. We are very proud of our partnership with Weights and Biases. We also, of course, a partner with NVIDIA. Yeah, you will have the time to check it out. Just a couple more words on what you might be interested in. We have a referral program. If you have some friends, you can get us connected, and then you have a reward according to these terms. Also, we have a self-service, so you can switch H100 in 5 minutes with only $25 to start, with no communication to sales or whatever, just by clicking into the console. Yeah. Also, to show you some companies that are using our cloud platform, maybe JetBrains rings a bell. Prisma Labs was one of the first proper Gen AI startups back in the day. We're proud to have some academia also with the London Institute of Mathematical Sciences and other guys. Yeah. But as I said, for self-service, you have to attach a credit card and pay $25. But for you, it will be. We'll also give you everyone in this room. We will give a $200 to just start, of course. In the end of today, we'll share the link on how to get these after the hackathon, of course. It's for your further projects. Yeah, I know for today I will switch to my great friend Idan. Yeah, I'm here. Andre from our team is also here filming. Thank you. Yeah, and maybe you have some questions. Thank you.
I wanted to offer sort of a testimonial. Like recently I went looking for, is there anywhere that I can rent a single H100 as opposed to 8, and then also that allows me to use the NCU profiler.
Yeah.
And Nebius was the only one that allowed that. So
that's right.
Yeah.
Thank you. Yeah, well, you have one. You can have just one H100.
Right. And you allow collecting profiling data.
Yeah, that's right.
Which is great.
Yeah.
NCU, like it's like computer.
Should you?
So I will just connect mine.
Yeah. Thank you, guys.
Okay. Okay. Bigger than I thought.
Okay. Excellent. Okay, guys, so it will be pretty quickly and pretty straightforward. I'm just going to explain a bit how. Yeah.
No.
Microphone. So, will you
Just leave it there.
Okay. So I'm just going to show you how to log into Nebius Cloud. It's very straightforward. Just
should people do this in real time?
Oh,
should we be doing this in real time?
Actually, I don't think that everyone has
guys,
a place to do that.
I think just like as an organizational note, so on the AGI House Hackathon Slack, there is a channel that you can find called hardcore-CUDA-hackathon. That channel already contains the PDF document that Idan is going to show you on how to connect to the pre-created accounts for all of you. I guess he also has a web page where you can get the credentials, right?
Yeah, exactly. So I just go over it really quickly. So in terms of creating and turning your brilliant projects into reality today, so you will need to get into to Nebius AI console, which you will need to just click on this URL. I just find some of you that try to copy and paste it to the URL, and I think that some of you just put an extra space in the URL. So just keep in mind, if there is an extra space, it won't work. So don't be panic about it. It will work. So just copy and paste it to your browser, and then you will need to get the credentials. Basically, I just created a dummy page that you will get the credentials. I will show you how it works. You can either click on this URL to get your credentials, or using the QR code. So basically, you will get this kind of web. You will just click on the get credential. You will get your credentials. Something really important, guys. Please use only one credential per project. Okay, so there is a limited amount for everyone today. So just keep in mind. Right after you will get your credentials, and you will click on this URL. So you can see that you will get into.
Yo, this guy's giving you free H100.
Yeah, free H100, guys. Thanks, dude. Okay, so you will get into this after clicking the URL, sign in with your received credentials, and then you will just migrate into this page, complete your account, just a regular registration with your email, and then you will get the full cloud console of Nebius AI. Afterwards, just create a new VM. You have all the documentations and links out here, so just keep in mind that following everything step by step, everything is described here. Also keep in mind that you're choosing the right image, and the right image with the pre-installed CUDA 12. So if you just wanted to install by yourself the CUDA, please avoid that and just use our own pre-defined images with included CUDA. Yeah, as
Is this 12 or 12.5 or just 12?
So I think it's 12.3, as I remember. Yeah. So as our friend remind us, we do have one single H100 VM options, and please, guys, use only 500 exactly for the SSD volume. Okay, that's super important. It's also mentioned here, but just keep in mind. Don't touch the network. You can do that, but just to keep everything simplest, just use the existing network settings. Put your own SSH keys. There is also documentation on how to do that. Basically, it's just a key gen, the generating key pairs with private and public. Yeah, basically everything is straightforward. One important thing I will just skip off because it's just reading it. So please just run the NVIDIA SMI command right after you generating the VM, just to keep to validate that everything is working correctly and the H100 is healthy and everything. Basically that's it. You have also documentation links on the bottom, and for every questions, our team is with the green t-shirt. You can't miss it. And yeah, good luck, guys. Any questions?
time, for 500 gigabytes, is it like the upper limit, or is like you need to use the exact 500?
Yeah, that's the upper limit. Yeah, you can use 10.
Okay.
It's the upper limit.
Don't put 10, just like the CUDA libraries and the compilers alone would be more than that.
That's right.
That's fair.
Okay, cool.
Big thanks to Nebius. Okay. Speaker talks are over. Hacker talks are here. We have 6 presentations prepped. So we're about to hear about attention-aware tensor memory acceleration, neural operators or diffusion models for fluid flow, Python search algorithm improvements, kernel Wolfram's physics model, and accelerating classical ML. So those 6 talks, all the speakers be prepped to go. It's going to be 1 minute per talk. So be ready to go. Chris, are you ready to go? Cool. Okay. This is Chris. He's going to give a talk on attention-aware tensor memory acceleration. If you would like to join him, take a listen.
Hi everyone, I'm Chris. We'll be working on a attention-aware TMA. So everyone knows about attention. It's a computational bottleneck in language model pre-training and inference. So there's been a lot of proposals to advance this, such as caching and flash attention, as we just heard. However, most of these advancements don't take into account the new Hopper microarchitecture. So we noticed a low GPU utilization on these chips. This was largely unaddressed until about 48 hours ago in the FlashAttention 3. So in my project, I'll be optimizing the tensor memory acceleration specifically for attention. And from what I've read, there's no overlap with the FlashAttention 3. So if this is something you're interested in working on and you like efficient training or PyTorch or CUDA or Cold Brew, feel free to talk to me after. So, perfect. Thanks everyone.
Ernst, neural operators.
Hi. Hi, my name is Ernest Young. By day, I'm a embedded flight software engineer in C++, but wanted to get more into CUDA. So this is more of a sales pitch to join a team or to have some throw around some project ideas. My background's in physics, so I was taking some kind of fluid simulation, and so looking at possibilities. There's neural operators. Really, if you're mathematically inclined, it's just the Fourier transform is based off Fourier series, and using that as like a basis to fill in weights. There's that. Maybe we kick around some diffusion models to simulate a fluid sim, but open to other ideas. Also, just adding on to like some of the talks I heard, really want to do something with Cutlass because it's related to the first talk. But yeah, thank you. Open to both joining team or creating a team. Thank you guys.
Jacob, updating the 6 degrees of Wikipedia Python.
Cool. Do you mind if I go to the site on this? Cool. My name's Jacob, founder of a company called Shortwave AI email app. I have a side project called 6 degrees of Wikipedia. It finds the shortest path in the link graph of Wikipedia between any 2 pages. The algorithm is written in Python. I have never written CUDA before. I want to use today to learn and port the algorithm to make it super fast. If it sounds interesting and anyone would love some teammates.
Okay, Jacob, as interested in kernel.
Oh, sorry. Yeah, Jared.
Oh, Jared, sorry, my bad.
No problem. So I'm an old kernel guy, and I've been with some of the other graybeards and so forth here, talking about the heterogeneous transformations happen over a little bit. The question that I've been kind of burn a hole in the back of my mind is, how do we start transitioning some of these traditional systems programming things into more of the compute model of a GPU? I want to do some benchmarks to see some of the low-hanging fruit that I'm is relevant to other side projects. But it's really a benchmarking job, trying to figure out the right intrinsics. I'm here with my daughter Pearl, because that's what we do. We do hackathons together. And anyone wants to join us and knows intrinsics, let us know.
Lev, on the Wolfram physics model CUDA optimization.
Yeah, so there's this project called the Wolfram Physics Project, which aims to find a fundamental theory of physics by studying hypergraph substitution models. So basically, you have a generalized version of graphs, and then you find subgraphs and replace them with other subgraphs. And there is currently an implementation which doesn't use the GPUs at all, and so it scales poorly. And if you have different places where you can substitute the graphs, it's very inefficient, and so we want to contribute to finding a fundamental theory of physics by implementing the graph substitution systems with GPUs.
Amazing project, amazing intentions. Stephen Wolfram actually was the key speaker for the last systems hackathon.
And I did that basically. I tried to do that at the first hardcore CUDA hack.
Oh, yeah. Yeah, that's some other problem. Okay.
So we should talk.
Okay, my turn. When I was teaching myself machine learning for the first time, I implemented almost every major like classical ML algorithm from scratch. And so this library is called Oracle. It has implementations of gradient boosted decision trees, of random forests, of multilayered perceptrons. And my intention for the hackathon is to take every single one of these algorithms, which are primarily implemented in Python and NumPy. So for example, here's an implementation of a convolutional neural network, sort of sets up a dense layer, convolution, prev deltas, activations. I want to basically translate this ML library into a CUDA accelerated variant that I benchmark against. So the question will be, can we, under a pretty short time constraint, come up with high quality CUDA implementations of each of these to a point where we get a speed up on all of these ML benchmarks. And so it should be a sort of tour de force in how to do classical machine learning with CUDA. Okay, final two, Kirill and then Justin on deck.
Hey everyone, I'm Kirill. I'm an engineer by day, do databases, but also by night and weekends I am doing the music production a bit, like as a hobby. And when you're doing the music production, there are a lot of like building components which are like you're taking for granted, like applying filters, like running convolutions for reverb or whatever. And it can be implemented in code, and you can do this in code on CPU with the libraries in Python like librosa or whatever. But it's also, I mean, all these building blocks like Fourier transforms and convolutions exist on CUDA, and we can use them. And basically, I'm curious whether I can get the audio track, upload it to GPU, process that, and get it back, and to get the same result as I would do on CPU. So if you have the feedback or you want to join and explore the world of sound, welcome.
Amazing. And last but not least, Justin on handwritten MMA compilers.
Yeah, hi everybody.
Oh,
sorry. Yeah, I work on LLVM and MVPTX at NVIDIA, and I don't really know how tensor cores work. So I wanted to do a project related to that. This is something I would like to do. Also would love to join other people's projects. And if anybody wants to do compiler stuff, would love to do that too. Yeah.
Okay. And with that, I guess some logistical details, and then I'll quick things off. There are two bathrooms. One's in this far left corner. The other is 2 floors down and around the corner. This is like a 4-story mansion, so feel free to spread out throughout this floor, the floor below it, and the floor below that. So like, all of them are open for hacking. Please take full advantage of it. Don't go upstairs. We'll probably cut it off because you see my movie coming down the stairs. Those are private bedrooms up there, so please do not explore upstairs. But feel free and please do go downstairs for your hacking. Lunch is set up. We have some LaCroix, some water, some Chinese food. More food will be coming, and make sure that you're in the Slack channel. So raise your hand if you're not in the Slack channel. Okay, if you're not in the Slack channel, come up after I'm done talking so that I can get you in the AGI House Slack, where we'll be releasing announcements about food and connections to all the links that you need to get access to the GPU, and where you can talk to all your collaborators and stuff. Do make sure that you get in the Slack. Yeah, this is the first CUDA specific hackathon that I've ever been at or heard of, so hopefully we can do something historic today. I'm really looking forward to seeing what people build and what kind of projects come out. But in my mind, this is, for a lot of people, an opportunity to get out of your comfort zones. Even if you work at NVIDIA, maybe there's something that you don't understand or that you're going to learn. There are fantastic people to learn from and create with. And so, yeah, give all of us the gift of your wonderful creative ideation. It's basically going to be 5.5 hours of hacking. Demos are at 8 o'clock tonight. So come to your creative idea accurately and efficiently, and burst it into existence. Actually, this is an awesome opportunity to come up with something new, build it, ship it, and hopefully everyone will have something phenomenal by the end of the day. So with that, let the first hardcore CUDA hackathon begin! Come up if you need Slack.
Not really.
Hello.
Bill, let me put my name. It's my email for Slack. Bill, hold a second. That's an energy drink.
Oh, really? Red Bull. Should be all
I'll put both of our names.
There's many mechanical elements, I just think we would have
Yeah.
One step at a time. We're I mean, we're going to be for a period of I'll find out how we're connected. Thanks, Jeremy.
Thank you. I appreciate it. That's my goal. I want to be like kind of a resource in this community. I want to it takes so much oxygen,
I just think that's part of that. So that's why I came out here. I'm more way more outside. They're hiring more people over here, trying to rent out. I kind of rent more technical. I was like, I'm like more figure out the pulse of like when you guys all that's why you guys know I really want to connect with them because I think it would be such a great resource for technologists to talk with. Maybe so yeah, we're also We are going to so every time we forget about it really is. So I'm excited about that. And also, I'm also I'm writing a story about
You have to think about the sound. Yeah, because we're giving a tour of a house without any visual. Oh, okay. Yeah, I gotta sit down. So this is the floor. The central part of the house is the library. 1,400 book library. It's the kind of omni-period religion not expect to physics type stuff to be actually economics and commercial. So if you have a desire for everything is special. We have an AI dedicated so the two fish shells so I think we upstairs, myself, Rohan, and Kyle and Tivgard, the founder of Multinon, was on the floor below this, and Patel, the founder of Unum, was on the floor. Founder of CUDA was forwarding. Got a lot of people. Is this normal? And so, like, I think with so many people coming into your house, sorry? So you enjoy it? Yeah. It's fascinating. I have a bedroom, so I don't it's very but I also have with a great view. Right, great view. Yeah, public works. So the reason I picked on this the first time I So what was it about the view of the city that you think was inspiring you? So I can show you the spot. Yeah. Oh, no.